SwayamPrabha. Digital India. Educated India.
Hello everyone. So in the last class we were talking about the different approaches, DNS, LES and RANs, isn't it? So let me just write that down again, DNS, LES and RANs. And we realized that that the cost and accuracy are different for these three approaches. So just briefly, let me just go over what each of the approach does. DNS or direct numerical simulation resolves all the length scales and time scales. So it is going to be computationally very expensive. We know that. Large eddy simulation or LES, what it does is it resolves all the large scales but models the small scales. So slightly less expensive, slightly less accurate compared to DNS. RANs on the other hand models all length scales because all it is doing is it is solving for the mean of the flow. It is solving for the Reynolds stresses. It is only solving for the mean of the flow. So it is modeling all the length scales. So it will be the least expensive and as a result, the least accurate. So the cost increases as you go from RANs to LES to DNS. And the accuracy also increases as you go from RANs to LES to DNS. So depending on what is more important to you when you're trying to solve a problem, you will have to choose between one of these methods. So we are listing out a set of criteria in order to appraise these different approaches. One is a level of description, 2, completeness, 3, cost and ease of use, 4, range of applicability, and 5, accuracy. And in order to make our point, in terms of looking at this criteria, we will look at two extreme approaches. One is the RANs-based approach, specifically what is called the mixing length model, which is one of the first models that are out there, that was developed. Mixing length model, and on the other extreme we have direct numerical simulation, which is the most accurate. What it does is it solves for the velocity flow field, which represents one realization of a turbulent flow experiment. That's what it does. So talking about the mixing length model, a mixing length model, again, it has been applied to statistically stationary boundary layer flows, and that was the basis of its development as well. It consists of the boundary layer equations for U mean and V mean, with the Reynolds shear stress and the turbulent viscosity obtained from the model equations given by the following. You have UV, which is the Reynolds stresses. UV mean is equal to minus nu T del Y of U mean. So this is the business hypothesis. What we are saying is that the turbulent stress or the Reynolds stress is proportional to the gradient of the mean of the flow field. That is what is written here. It is proportional to the gradient of the mean of the flow field. So if it is proportional to that, the constant of proportionality is, business argued, could be some kind of coefficient, just like you have it for the Newton's law of viscosity. Here also you could have some kind of viscosity which we call the eddy viscosity or the turbulent viscosity. We have discussed the business hypothesis earlier. This nu T, now this expression here is in general. Any Reynolds stresses is expressed as a function of the mean velocity gradient. And the constant of proportionality is always the turbulent viscosity or the eddy viscosity. Now note that this violates one of the features of turbulence, isn't it? As we had discussed in some of the earlier modules. Turbulence is not a property of the fluid, it is a property of the flow. So the fact that we are using it violates that feature. However, this is and business warned of that as well. When he introduced this hypothesis, he warned us of that. But even to date, we have been using this particular relationship. in terms of coming up with the Reynolds stresses. And this is especially true in the case of a RANS approach. So we are saying that the Reynolds stresses is proportional to the mean velocity gradient, and the constant of proportionality could be a coefficient like the eddy viscosity. This is true for all RANS type models. Now the way nu-t or the eddy viscosity is specified, that depends on your turbulence model. And here we are considering the mixing length model for discussion. So the eddy viscosity or the turbulent viscosity is given by this expression here in the mixing length model. What is it? It is equal to Lm squared and the modulus of del y of mean velocity, where Lm is what is called the mixing length, and this is specified usually as a function of position. Sometimes it is specified to be a constant, although that might not be the case. So sometimes it is just taken to be a fraction of the characteristic length scale of the flow. So what we are saying is nu-t is Lm squared del y of mean of velocity. Now the mixing length model has a very interesting history. The analogy of the mixing length model comes from kinetic theory of gases. Again, a fluid property, not a flow property. Kinetic theory of gases has to do with what the fluid is. So in kinetic theory of gases, the idea is one molecule has a certain amount of energy. It travels over a certain distance called the mean free path before it bombards another molecule and transfers its energy to the other molecule, isn't it? That's based on the kinetic theory of gases. Now here what we are saying is a fluid particle travels a certain distance before it imparts momentum to the other fluid particle. And that is how the energy gets cascaded from the large scales to the small scales. That is the argument. So that length over which it travels before it imparts its momentum to the neighboring fluid particle is called the mixing length. And that is the analogy for the mixing length model. So that mixing length is assumed to be a function of space and time. Sorry, not time, but a function of space. But in some cases, in the simplest of scenarios, it is just considered to be a fraction of the characteristic length scale of the flow. So that's what we have. So these are your equations. These equations basically close out the Reynolds equations. The Reynolds equations, if you remember, are averaged Navier-Stokes equations. When you average out the Navier-Stokes equations, you get the Reynolds equations, and you have terms that are unclosed, terms that you don't have a way to solve. That is the turbulence closure problem, remember? And for that, you need a specification of the Reynolds stresses. That is where a turbulence model comes in, and specifically here, the mixing length model comes in. So I hope this is clear. So this is your mixing length model specification. Now, let's look at the very first criteria. So you know what a DNS is. Now you know what a mixing length model is. Let's look at our first criteria, which is the level of description. So in DNS, the flow is described by U of xt, and all other information can be determined from it, isn't it? All you need is the velocity at every point in space, at every point in time, and you have the entire flow field at all points for one realization. So that's all you need. You can calculate means from that, you can calculate gradients from that, you can calculate any kinds of statistics from that, multi-point statistics, multi-time statistics, you can examine turbulent structures. That's all you need. You just need the velocity at every point in space and time. That's it. That is the level of description in DNS. There's nothing more to be specified. In the mixing length model, on the other hand, you are describing only the mean flow. Your level of description is at the mean flow level. So apart from specifying the mixing length, the only quantities that are represented are U mean and V mean. We are talking about a boundary layer flow, so the third direction is not valid or is assumed to be negligible. So we are only considering X and Y direction, for example. So U mean and V mean. That's what we mean by this. U mean and V mean. No information is provided about PDFs of velocity, 2-point correlation, turbulence structures, nothing. Your only level of description is the mean velocity, U mean and V mean. So this kind of limited description by mean flow methods like RANS type methods such as the mixing length model can be sufficient in many applications. In a lot of engineering applications, maybe all we care about is the mean. And the argument here is that for using such a model, the argument here for using such a model is that the mean flow field can give you a lot of information about certain designs. Maybe at the design level, that is all you need, the mean. So this can be adequate in many applications. Now, even between turbulence model, one can be more accurate than the other. We are not getting into that here. So the mixing length model, we picked a very extreme RANS based approach. One of the first models that was developed. It's an algebraic turbulence model. It was one of the first turbulence models that was developed, and it is probably the least accurate, if you will, by all standards. So models like standard K epsilon, K omega, the Reynolds stress model, RST, those are all supposed to be more accurate than the mixing length model. However, this mixing length model has been used for decades for aerodynamic design. So imagine that a model which is not as accurate, where you only get the means, has been used in a lot of engineering applications. So it has been shown to be adequate for a lot of applications. But to date, with all that we know about turbulence, with all that we know about turbulence modeling, with all the computing resources that are out there, these kind of models are hardly used. So that is as far as the level of description is concerned. DNS versus the mixing length model. The next criteria is related to completeness. Now, what does completeness mean? A model is deemed complete if its constituent equations are free from flow-dependent specifications. So you have your Navier-Stokes equations, isn't it? So I'm going to just to describe this, I'm going to write it out. So I have ut plus u dot del u, and again all of these are vectors, is equal to minus 1 over rho del p plus nu del squared u. Now I have the velocity field which I'm solving for, and I'll just take the Navier-Stokes equations here. Obviously pressure needs to be specified through the Poisson's equation for incompressible flow, but I'll not get into that. I'll just consider the Navier-Stokes here. Now, if I were to solve for this equation like I do in a DNS, I get the velocity field for every point in space and time. The only thing I need to specify in this equation are density and viscosity. So properties, material properties. Material properties are all that I need to specify, rho and nu. And then in addition to that, of course, mathematically to solve these equations, I need what are called initial conditions, because I'm solving a time-dependent equation, and boundary conditions. I need to have initial conditions and boundary conditions. What is the velocity on the pipe surface, for example? In a channel, what is the velocity on the channel surface? It is 0, of course, because of the no-slip boundary condition. So those kind of boundary conditions I will need to specify. If I have flow in a jet, what is the velocity at which flow is coming in through the nozzle? That is your boundary condition. I will need to specify that. So those boundary conditions have to be specified, but in order to solve this equation, all I need to do is to specify the material properties. No other flow-dependent specifications have to be provided. No other flow-dependent specifications have to be provided. In that sense, DNS is complete. You don't need to provide anything else. Material properties are the material properties. If you're solving for water, provide the density and the viscosity. If you're solving for air, provide the density and the viscosity. On the other hand, if we think about the mixing length model, it is incomplete. Why? Because the mixing length has to be specified. Where do you get that mixing length from? What kind of approximation do you come up with for the mixing length? We don't know what the mixing length is. That is why I was saying earlier, in the simplest of scenarios, the mixing length is specified as a fraction of the characteristic length scale of the flow. So in that sense, the mixing length model is incomplete because it cannot stand on its own. There has to be some specification that is provided. Now, what is wrong with this, right? What is wrong with the model being incomplete? The mixing length model has been used widely for a lot of different applications in the past, maybe not now, in the past. And then what is wrong with that? So the thing is, incomplete models, they can be useful in a narrow class. For example, in the case of a mixing length model, it has been used successfully with reasonable success, I should say, for attached boundary layer or airfoils. And then here, what you will have to do is, in order to specify the mixing length, you will need to have some sense of what the mixing length could be in these applications. Where does that information come from? It comes from experiments. Some kind of semi-empirical knowledge would be required in order to specify the mixing length. So the model as such is incomplete, right? Because it cannot solve on its own. You will need some additional supplemental information, and that could come from experiments, that could come from some analytical theory. Either way, it's incomplete. So in the case of airfoils, this mixing length model has been used, I was saying earlier, for a lot of aerodynamic design in the past, decades ago. And the specification of the mixing length used to come from aerodynamic measurements. So that mixing length will have to be specified, and then the model becomes complete with that supplemental information. So in general, completeness is clearly desirable, because what works for aerodynamics might not work for internal flows, pipe flows. So the same mixing length that you specify in a mixing length model calculation, which you probably got from experimental measurements in aerodynamics, and you get that, and then can you apply that to pipe flow, to a turbulent pipe flow? Technically, you cannot. Right? Technically, you cannot, because you have based that on information from aerodynamics. That is the difference here. So that is the problem with incomplete, that is a problem with having an incomplete model. So that's what we mean by, in general, completeness is clearly desirable. Next, cost and ease of use. So I've provided a table here. Okay, the left hand side of the table provides the dimensionality of the flow. Then the first column. The second column is the boundary layer, which is basically what kind of, whether it is statistically stationary flows or not. So we are talking about boundary layer flows, a class of boundary layer flows. The third column is whether it is a set of statistically stationary flows, which can be, you would think, simpler to solve. And the fourth column shows examples of not statistically stationary flows. I'll come back to this table. But what we are trying to say is the computational difficulty increases with the statistical dimensionality of the flow. That is for sure. As you go from 0D to 1D to 2D to 3D. What do I mean by 0D? It means it's a homogeneous shear flow, so nothing is changing with respect to space. You only have a mean, you only have a single value that you're solving for. So it is not changing with respect to space, not in 1D or 2D. 1D, on the other hand, if you have a fully developed pipe flow or channel flow, like you have here, then it could be 1D. Temporal mixing layer, where you have a mixing layer that is changing with respect to time, that could be 1D. 2D, a flat plate boundary layer flow, a jet in a co-flow, these are examples of 2D. Flow through that is statistically stationary, and boundary layer approximation applies here. The boundary layer approximation applies here in these cases. It is 2D, but boundary layer approximation applies here. Now, a scenario where boundary layer approximation does not apply and is statistically stationary is flow through a sudden expansion in a 2D duct. And A flow where boundary layer approximation does not apply and is not statistically stationary is a flow over an oscillating cylinder. Now you go to 3D, boundary layer on a wing. Here also boundary layer approximation applies. Something that boundary layer approximation does not apply and is statistically stationary is a jet in a cross flow or flow over an aircraft or a building. 3D, isn't it? But statistically stationary. Something that is where a boundary layer approximation does not apply and it is not statistically stationary is flow in a cylinder in a reciprocating engine. So as you can see, as I'm going from the left top corner to the bottom right corner, my complexity is increasing. Why? Because my dimensionality is increasing from 0 to 1 to 2 to 3. It is my boundary layer approximation is no longer holding. It is becoming more like a statistically stationary flow without the boundary layer approximation, and on the other end I am getting a not statistically stationary flow. So that is harder to solve. I have to solve it with respect to time. So this is what I mean by the computational difficulty increases. So it decreases if the flow is statistically stationary and decreases further if the boundary layer equations can be used. So if you can use a boundary layer approximation, it's relatively simpler. So that is what happens when you're using a mixing length model. So that is what I mean by cost and ease of the use. So the ease at which you can apply a model, the cost associated with it, all changes depending on the complexity of the flow, the complexity of your the particular problem, the approximation you can make. So here what happens is, in approaches like DNS, the cost is rapidly increasing as a function of the Reynolds number of the flow. So as the Reynolds number increases, we saw earlier there was a statistic showing the cost increases with RE cube, and we will look at how that relationship works in the next in this module over the next few classes. But the computational cost increases as a function of the Reynolds number of the flow, whereas in mixing length model, since all length scales are just modeled and not a single length scale is resolved, the cost due to an increase in Reynolds number is insignificant, as in the increase in cost is insignificant. It's basically, there's no dependence on the Reynolds number. You are using a mixing length model for a turbulent flow, period. As long as the flow is turbulent, it doesn't matter, it almost doesn't matter what the Reynolds number is. Because the mixing length model is only coming up with the mean. No length scales are resolved anyway, no matter what the Reynolds number is. So then why does it matter? The cost wouldn't matter depending on the Reynolds number. That's what we mean by that. But the ease at which you can solve this, that depends on the kind of problem you have, and that depends on the kind of complexity you have in the problem. So you have the task of performing a turbulent flow calculation. You can consider it in two parts. So we are talking about what is the ease associated with using a model, right? We are talking about two parts here. One is the development or obtainment of a computer program to solve the model equations and set up the flow initial conditions and boundary conditions. So that development, sometimes you will have to develop your code on your own. Sometimes there are open source codes that are available. OpenFOAM is an example of an open source code. There are a lot of academic codes that are out there that are available for use for academic purposes. You can use some of those. Trying to find the right code to use for your particular problem is another challenge. So that's what we mean by it. So that there is a cost and an effort associated with obtaining a code. Developing a code for sure, developing a code from scratch sure has its own efforts. But even obtaining the right code appropriate for the problem that you're solving is also a task. Right? So obtainment of a computer program to solve the model equations and set up the flow boundary conditions is a task in itself. That's the first part. Second part is, once you develop the code or once you obtain the code, the execution of the computer program to perform the calculation and extract the results. What does that mean, right? So even if you set up the code, set up the boundary conditions and the initial conditions and try to solve it for your particular problem, you're going to probably run into a lot of issues, possibly computing resources, possibly convergence issues, possibly related to round-off errors on your computer, precision errors, and repeatability of the program, of the solution of the equations. You're going to run into a lot of such issues. So those two are the most important things in terms of the cost and the ease of use. Now, as far as the cost and difficulty of the first step is concerned, it depends on available software, algorithms, and all of that depends on the kind of problem that you're solving, isn't it? The effort required to develop a program can be significant, but that cost is a one-time cost. But if you're obtaining a code, at least the development part is not there, but you will still have to set up the boundary conditions and initial conditions for the problem that you're solving. Now for the second part, the execution part, the cost and difficulty of the second part, performing the computation, depends on what kind of computer you're using. What kind of skill levels do you have? Do you or your team have? Right? Do you have the right amount of skills to perform the computation, and do you have enough computing resource to run the program that you have developed or obtained? Sometimes certain codes are more memory intensive. So then do you have the resources to do that? So those are the two questions we need to be asking when we are considering this particular criteria, the cost and ease of use. We will actually delve more into the cost and ease of use because this is the right time for thinking about what is the actual cost associated with using these kind of models, what kind of computing resources should I be thinking about, and what kind of programs should I be thinking about. We will delve into that in the next class. Thank you.